I'm probably going to annoy Kevin a bit because I'm going to talk about net zero. And but I actually bought my first electric vehicle about 2 months ago, and I think it's something. I think I'm right in saying something about I've got to drive it for about 7 years or 10 years or something before I actually make any impact on reducing my carbon emissions because of the embedded carbon in the manufacture of that vehicle. So if we're going to achieve our reduction in greenhouse gas emissions by 2050 or whatever date, it's crucial that we have to decarbonize industry. And this includes the carbon intensive sectors listed here. In addition to dealing with climate change, it's important that this is consistent with sustainable economic growth and for the UK to improve its international competitiveness, whilst still making huge changes and transitions to net zero. We have to be very careful how we achieve this because of the the products that we manufacture are traded internationally and have relatively low cost margins, and any small increase in production costs could greatly reduce market share. Rightly, this agenda is framed as dealing with climate change, but it's also importantly addressing security of supply, air quality, and also health outcomes. We have the opportunity to exploit world-leading innovation in technology, engineering, and new business models to transform our vital industrial sector. Over the next decade, there needs to be a significant switching to alternative energy sources and vectors. This will include greater use of renewable electricity and greater electrification of production processes. There will be the prospect to exploit solar and geothermal energy and the switching to hydrogen and other hydrogen carriers, such as ammonia, biomass, and synthetic fuels. The UK government aims to encourage around 20 terawatt hours to be switched to low carbon and zero carbon vectors by 2030. Although there has been significant improvements in energy efficiency and reducing energy demand over the last few decades, there is still much more that we can achieve. There is a huge opportunity to recover, store, and use waste heat, for example. The use of this heat can be facilitated by thermal storage, and in particular benefiting from advances that are being made in latent and thermochemical storage. This heat can be used to generate electricity and using low temperature thermodynamic cycles, or produce cooling, or being thermally upgraded to higher and more useful temperatures. Heating and cooling networks can be used to provide energy services elsewhere. There's also the need to switch to alternative low carbon feedstocks and alternative industrial processes so that we can take advantage of the circular economy, which was mentioned earlier, and the energy vector switching. We also need to build on industrial symbiosis that already exists and takes place in our industrial clusters, and to extend the use of byproducts and waste as a feedstocks for others to use. As seen here in this table, industrial processes use enormous amounts of high temperature heat energy, currently provided through the combustion of coal, oil, and natural gas. The main fuel switching options are shown in the figure below. These are the combustion of hydrogen and the use of natural gas and biomass, both with carbon capture, and also through the greater use of electrification, and to a small extent, I think, nuclear heat. Hydrogen is particularly of a focus since it is similar to burning natural gas in many respects. It produces no emissions at the point of use, carbon emissions, and it is possible to achieve flame temperatures of 2,100 degrees C when combusted in air, or even 2,800 in oxygen. electrical heating options are able to achieve around 1,800 degrees C and can take advantage of zero carbon electricity. The advantages of electrical heating methods are that they can provide controllable and precise heating, greater temperature flexibility, and the potential to require less maintenance. However, they require very often very expensive changes to production processes. The UK industry accounts for equivalent of 72 million tons of CO2 per year. That's about 16% of the UK's greenhouse gas emissions. Globally, it's about 24% and still growing. And it is not straightforward to decarbonise. Almost half of these emissions in the UK occur in 6 industrial regions or clusters, shown here. These clusters are where the UK's iron and steel, refinery and chemicals industries are mainly concentrated. These sectors have their own specific challenges and require a range of measures to decarbonise, but there is a great opportunity to work collectively with these clusters to deploy new solutions. It's not possible to change all plants at a pace because of disruption to production and the massive capital investment involved. And some current processes aren't possible to decarbonise completely. And therefore, carbon capture, utilisation and storage, CCUS, must be deployed to prevent atmospheric emissions. CCUS is vital, and the UK government is supporting the drive to capture and store, I think it's around 3 million tonnes of CO2 per year by 2030. The UK has the advantage in its geology, and there are opportunities to store vast amounts of captured CO2 offshore in the North Sea and the Irish Sea. Durham Energy Institute has been working with all the industrial clusters, but in particular Teesside. Teesside focuses on chemical and petrochemical and bioprocessing, and is the most compact and integrated of the 6 major industrial clusters in the UK. It covers less than 200 square kilometres and it has fantastic integrated infrastructure across the whole site. Therefore, it's arguably the most suitable to be the first to transition to net zero emissions. The current UK government goal is to create 4 low carbon clusters by 2030, and at least 1 to be completely net zero by 2040. The yellow lines on the cluster map show pipe corridors which interconnect to the individual industrial companies operating within the cluster. This infrastructure supports industrial symbiosis, facilitates the integration of CCUS, and allows the distribution of hydrogen across the site. Teesside also benefits from very close proximity to offshore CO2 storage and offshore wind, as I've already talked about, in the southern North Sea. CF Fertilizers has an integrated production and storage facility for ammonia and nitric acid, supporting chemical processing companies across the cluster and producing fertilizer. To get a sense of the scale, I've been told that this uses the same amount of natural gas as Manchester. Saarbeck is Europe's 2nd largest ethylene cracker and the world's largest low-density polyethylene plant. Hydrogen is a byproduct from their production processes, and it has now made fuel switching modifications to use hydrogen instead of natural gas to provide heat across their plant. The BOC steam methane reformer produces around 32,000 tonnes of hydrogen per year to supply industrial operations across Teesside cluster. This is distributed by around 70 kilometres of hydrogen pipelines. Through the Net Zero Teesside project, it is planned to integrate carbon capture to this plant and additional large-scale reformers to produce blue hydrogen. There are also plans for large-scale electrolysis on site to produce green hydrogen. The Net Zero Teesside is a CCUS project which is led by BP, who are working with ENI, Equinor, Shell, and Total. The aim of this project is to exploit the existing pipe infrastructure and the large industrial companies who are keen to decarbonize on Teesside. Both these existing hydrogen and ammonia productions on Teesside provide high concentrations of CO2 as a byproduct, about 1 million tons per year. So it's very cost effective to capture, utilize, and store. This creates the opportunity to produce large amounts of blue hydrogen and blue ammonia, as previously mentioned. So there is something like another 6 million tons of CO2 per year produced on site, which can also benefit from the net zero project, Teesside project. In addition, a new combined cycle gas turbine power station is to be built, and its CO2 will be captured. Storage of the CO2 will be through compression and dedicated pipeline to the Endurance saline aquifer, which is around 145 kilometers offshore. I'd like to briefly mention a few projects which Durham Energy Institute are conducting, which relate to industrial decarbonisation. We are exploring a number of routes to utilize captured carbon. One example shown here is a new pathway for the production of PEF, which is a replacement for polyethylene material made from using waste biomass and captured CO2 from other industrial processes. We are exploring the production of hydrogen and chemical feedstocks by the controlled anaerobic fermentation of biomass waste streams. We are developing biomass gasification technology with integrated carbon capture to produce hydrogen and synthetic fuels. These are some examples of our research to improve industrial energy efficiency. We're developing intelligent heating and cooling networks using absorption technology and thermochemical fluids to recover and use industrial waste heat for energy services. We are moving towards commercialization of novel sorption and hybrid heat pump technology to recover and store low-grade heat and to convert it either into electrical power, cooling, or higher temperature and more useful heat. Also, we have been developing phase change materials and thermochemical systems for long-term storage of waste heat, of solar, thermal, and geothermal energy. Finally, there are some examples here of our hydrogen-related research and development work. We are conducting a series of techno-economic studies covering the production, storage, distribution, and use of hydrogen. For at least 15 years now, we have been conducting research programs on the combustion and oxycombustion of hydrogen for combined heat and power and other applications. We are leading the development of a new distributed energy hub concept, which integrates hydrogen-fueled combined heat and power and heating and cooling networks and refueling of transport. Also, we are building research and demonstration facilities to improve energy efficiency of electrolysis and also to improve the efficiency of gas compression, particularly of hydrogen. These are just a few examples of the type of work that Durham Energy Institute is currently involved in. So to summarize, industry accounts for around a quarter of all of the UK greenhouse gas emissions, and more than 2/3 of these emissions come from our energy intensive industries. So it's pretty clear that whichever energy system pathway we take, greater electrification, the use of hydrogen, CCUS, they'll all play an important role in industrial decarbonisation and our net zero ambitions. I think the key challenge is to do this whilst we can increase our international competitiveness. There's a lot of changes already happening. There are huge programs of research and development and a lot of demonstration projects. which are tackling industrial emissions. But this work must be urgently accelerated if we're going to meet our net zero commitments. And the next 10 years are crucial. And we must get on with it. So with that, I'll finish and thank you for listening.